Hello. In this video lecture, we will see 1D study no heat generation conduction in hollow sphere. So I have drawn a diagram here of hollow sphere. So you can see it's a cross-sectional view. The inner radius is Ri and at the inner surface the temperature is Ti. The outer radius is Ro and at the outer surface the temperature is To. Now let us go to the assumptions. So we are saying that it is 1D. So the temperature will not vary in the other two directions. So we are considering the other two directions at the phi and theta. So temperature will not vary in phi and theta. Next, study. Therefore, the temperature at any point will not vary with time. Generally, we have temperature as a function of space and time. That is in this case, capital R. That is in this case, a radius, phi, theta, and time. So according to our assumption, temperature will be a function of radius only. That is, the temperature will vary only in the radial direction. Now we'll go towards the governing equation. So we'll go towards the governing equation. So we have the governing equation 1 by r square dou by dou r square dou t by dou r plus 1 by r square sine theta dou by dou theta sine theta dou t by dou theta plus 1 by r square sine square theta dou 2 t by dou phi square plus q by k equals to 1 by alpha dou t by dou t. R is the radial direction, theta is the zenith angle, and your phi is the azimuthal angle. Then your q is the heat generation rate. So dou t by dou theta will be 0 because t is not a function of t. Dou 2t upon d phi square is 0 because t is not a function of phi. No heat generation, so q is 0. And temperature at a point is not changing with time, so dou t by dou t is 0. So you get 1 by r square dou by dou r bracket r square dou t by dou r equals to 0. From where we get dou by dou r square dou t by dou r is 0. Since temperature is a function of r only, your partial derivative become exact and we have d by dr bracket r square dt by dr is 0. We will integrate it once, we will get r square dt by dr equals to c1. We will rearrange it, so dt by dr equals to c1 upon r square, and we will again integrate it. We get t equals to minus c1 upon capital R plus c2. Now we need, since there are two constants, we will need two conditions of t with respect to the radius. So we will go to the boundary conditions, that is at the r equals to ri, the inner surface t is ti, at r equals to ro, that is the outer surface t is to. So we will substitute in the equations and we will get the equation like ti equals to minus c1 upon ri plus c2, t0 equals to minus c1 upon r0 plus c2. From there we get c1 and c2 values. We will substitute these c1 and c2 values in your general solution, and from there we get the temperature distribution in this form. So you can see here that the temperature T varies with R in hyperbolic manner, okay, because T and R has a reciprocal relationship, so they will vary in the hyperbolic manner. We will try to draw now the temperature profiles. Okay, so temperature profile. So for the temperature profile we will need dt by dr. So we have taken dt by dr and the temperature distribution. So from here we can draw the conclusions that for the case of Ti greater than T0, your dt by dr, that is slope, is negative. Then your slope reduces as R increases and your temperature reduces as R increases, and you will get this type of diagram in the case of Ti greater than T0. So this is a temperature profile. Okay. So from the diagram you can see the temperature is reducing as R is increasing, your slope is reducing as R is increasing, and throughout the slope is negative. Then go for the heat transfer rate. So we will go for the case of Ti greater than T0. So the heat transfer rate Watt will be Q, which is minus Ka dou T by dou R at any R. So this is for Ti greater than T0, that is the heat transfer will be radially outward. So therefore there is a minus sign in front of K. We have written dou T by dou R at any R because this is a case of steady plus no heat generation. So the Q value will be same at any R value. We have taken A as 4 pi R square, that is the area perpendicular to the radial direction, and from there we get Q equals to Ti minus T0 divided by R0 minus Ri divided by 4 pi k R0 Ri. If we go for T0 greater than Ti, the denominator will be same, just numerator is T0 minus Ti. Okay. And when we compare it with the electrical terms, that is I equals to delta V by R, we can say that this delta T in the numerator is compared with the voltage difference, heat transfer rate with the current, and the denominator is the thermal resistance which is compared to the electrical resistance. Thank you.